In 1915, Albert Einstein completed one of the most profound theories ever created, a theory that changed our understanding of gravity, space, time, and reality itself. According to this theory, gravity is not a force. Planets do not orbit the sun because they are pulled. Instead, they are following the curves of space-time. This idea became known as general relativity, but beyond physics it raised deep philosophical questions. What is gravity really? Is space-time a physical thing? Does geometry describe reality itself? To understand the philosophical revolution behind general relativity, we have to start with a simple question. Why do objects fall? For over 2 centuries, gravity was explained by the theory of Isaac Newton. Newton's law of gravitation said that every mass attracts every other mass. The force is given by this equation. This equation worked extremely well. It explained planetary orbits, falling objects, tides, and comets. But Newton himself admitted something troubling. He did not know what gravity actually was. How could objects influence each other across empty space? This mysterious phenomenon was called action at a distance. Many philosophers found this deeply unsatisfying, and Einstein would eventually replace it. Around 1907, Einstein had what he later called the happiest thought of his life. He realized something simple but profound. If you are falling, you feel weightless. Imagine an elevator falling freely. Inside the elevator, objects float, gravity seems to disappear. This observation became the equivalence principle. The principle states gravity and acceleration are indistinguishable. This insight became the foundation of general relativity. Einstein proposed a radical new idea. Mass does not create a gravitational force. Instead, mass curves space-time. Objects move along the straightest possible path in curved space-time. These paths are called geodesics. A planet orbiting a star is not being pulled. It is simply following the geometry of space-time. Einstein summarized the idea elegantly. Matter tells space-time how to curve, space-time tells matter how to move. This transformed gravity from a force into a geometric property of reality. To describe curved spacetime, Einstein relied on advanced mathematics. Much of it came from the work of Bernard Riemann, who developed the mathematics of curved spaces. Using this geometry, Einstein derived the Einstein field equations. These equations describe how matter and energy shapes spacetime. In simplified form, they look like this. On one side of the equation, the geometry of spacetime. On the other side, the energy and matter within it. Philosophically, this equation suggests something extraordinary. Geometry is not just mathematical, it is physical reality. General relativity made several bold predictions. Many of them were later confirmed experimentally. 1. Bending of light. Gravity can bend light. This effect is known as gravitational lensing. It was confirmed during the 1919 solar eclipse by Arthur Eddington. The discovery made Einstein world famous overnight. 2. The precession of Mercury. The orbit of Mercury shifts slightly over time. Newton's theory could not fully explain this. General relativity predicted the correct amount. This was one of Einstein's earliest triumphs. 3. Black holes. General relativity predicted objects so dense that not even light can escape. These objects became known as black holes. They were once considered theoretical curiosities. Today they are a central part of modern astrophysics. General relativity didn't just solve problems in physics. It raised profound philosophical questions. Is space-time real? Is space-time a physical entity? Or is it just a mathematical description? Philosophers debate two views: substantivism, space-time exists independently of objects, or relationism, space-time is just a relationship between objects. Einstein's theory seems to favor substantivism. Space-time can bend, ripple, and even propagate waves. What is geometry? Before Einstein, geometry was considered purely mathematical, but general relativity suggests geometry is physical. The structure of space-time determines how objects move. This blurred the boundary between mathematics and physics. The nature of gravity. If gravity is not a force, then what is it? General relativity suggests gravity is the shape of reality itself. This is one of the deepest conceptual shifts in science. Einstein believed physics should aim for deep conceptual simplicity. He often criticized purely empirical approaches. Instead, he argued for theories guided by mathematical elegance, conceptual clarity, and unification. His philosophy of science was closer to rationalism than empiricism, yet his theories ultimately succeeded because they made testable predictions. General relativity describes gravity beautifully, but it has a problem. It does not work with quantum mechanics. Quantum theory governs atoms, particles, and radiation. General relativity governs stars, galaxies, and the universe itself. But when both theories apply, such as inside black holes, they contradict each other. This leads to one of the greatest challenges in modern physics, quantum gravity. General relativity changed our understanding of gravity. It revealed that space-time is dynamic. It bends, stretches, and evolves with matter and energy. But it also raised deeper questions. If space-time can curve, if black holes exist, and if gravity is geometry, then what happens when space-time itself becomes quantum? This question leads to the frontier of modern physics.